Okay, I think we are live. So welcome everyone to Static Analysis Days again. My name is Walter Capitani, and this talk today, the last talk of the show, is about performing a security review on unknown code. And I'm really pleased to be joined today by John Blattner from Imagix, and I'm going to let John go ahead and introduce himself.
Thanks, Walter. And I'd like to thank all of you in attendance for your time and for your interest in this subject. My name is John Blattner, and in this session, I'm going to be presenting a middle part about reverse engineering and the role that it plays in the challenge of conducting security reviews of unfamiliar code. I've been involved in the field of reverse engineering of source code since my time at Cadre Technologies. Cadre was a case tool company focused on modeling software, and I was involved in reverse engineering source code into those models. Here, I'm one of the founders of Imagix, and our focus is on reverse engineering of program understanding and transforming existing source code from a resource drain into a major asset. Walter?
Thank you, John. So before we get started, just a quick introduction for myself. I did speak yesterday, and I am part of the organization at GrammaTech, part of the product management team here, helping guide the roadmap and future development of the CodeSonar and CodeSentry products here at GrammaTech. So with no further ado, let's get started. Talking about security reviews on unknown codes. So definitely myself as a developer, as a troubleshooter of code, helping companies figure out why their code's not working well or what kind of problems it might have in it. I've had the feeling that this gentleman does here on the screen, which is, you've got a lot of inputs, you're unfamiliar, let's say, with the body of code, and you're trying to figure out even where to get started. And so today we're going to talk about tools and techniques that can help you with that task and help you identify security vulnerabilities in unknown code, how to pick apart that code and visualize it, understand it, make sure you are testing it properly, and really get a full security picture of that code. So we kind of have a few problems here with the security review. So we've got the large body of source code. This could be tens of thousands of lines of code in an embedded project to maybe millions of lines of code in a really big enterprise piece of software. Today you might have open source code that is integrated into that. So you're jumping in and out of function calls from open source code that maybe itself has tens of thousands of lines of code, or API calls to operating system functions. A lot of the time, we have little to no architecture information about the code. So, sometimes, developers start out with good intentions, or architects where they're designing code and they, write down some diagrams or flowcharts or things like that. But then over time, as the pace of development increases, sometimes that documentation gets stale, gets left behind, and we don't keep it up to date. So you read it and it gives you maybe a few pointers, but it doesn't really have the full picture. Or, what we've been asked to do is say, give us a report on how much better the software is than before. Have we introduced new security vulnerabilities? Are there, what do we have for existing vulnerabilities that we've corrected? So your management team or your customer is asking you to figure out this delta, again, about a body of code that you have no knowledge. As is typical today, we're shortening our iteration times in development, so the amount of time you have to perform this review is typically getting shorter, right? You've got, particularly if it's at the end of a development cycle, that someone's coming to you and asking you for this, you don't have a lot of time to get to know the source code and review it, review the changes, so you need tools that can help you in that time window. And so we'll talk today about these tools, how can they work together, exchange information, and perform various tasks to help with performing that security review. So we have these two big problems, right, we've talked about so far. We've got the whiteboard problem. That's what you know about the code on the left. You know exactly nothing. So you've got this blank page, and you're trying to fill out in your mind, develop a model of the code, the architecture, where the inputs are coming in, where you're going to third-party code or outside code that you've got to validate. You've got that on the one side. And then in front of you, so that's what you have in your brain, is the blank part. And in front of you on the screen, you've got that bowl of spaghetti and meatballs, right? And even if it's well-written code, when you put 10,000 lines of code in front of somebody, it kind of looks like that at the start. And you're not sure where to start picking on that to pull that thread of like, what's my main execution thread, for example, or where do I get inputs from a messaging program, from another process, that kind of thing. So these are the challenges we have, is we don't really know where to even start on that. And I apologize, it's late afternoon in Europe, so I'm sorry for putting a nice bowl of pasta on the screen. People are going to be getting hungry about this time of day. So the tools we're going to talk about today are static analysis tools. So, for example, GrammaTech is the creator of the CodeSonar tool. It's a well-regarded, very highly advanced static code analysis tool that's been in the field for many years and provides a lot of warning class detection on various types of quality and security issues in your code. I'm going to hand it over to John in the middle of the presentation, who'll talk about reverse engineering tools and how those can help with security analysis. And then we're going to talk a bit about code coverage tools and visualization. So let's jump right in to the static code analysis portion of this presentation. So I know you've heard, hopefully heard from our VP of Engineering, Paul Anderson, about static code analysis. So we won't focus too much on the technology of static code analysis, but rather on what kind of warnings and defects it can show you. So there's kind of two aspects to static code analysis results. The first would be what we could call the quality metric. So this is based on coding standards and best practices in the industry using sets of coding rules, for example, like the MISRA rules developed by the automotive industry, or the JPL set of coding rules, or the CERT-C security rules, and others, numerous standards that are supported by CodeSonar. And they really are quality metrics. Even though some of those do cover security, you're really scoring against a metric of kind of a compliance, right? And these are good as an outset to say we've reduced the number of issues of this type, and we don't have any issues of this type in here. But they don't necessarily always cover everything that a static code analysis tool can find that would be related to security. So the second set of rules we can look at are those that specifically detect bad behavior from a security perspective. So we're talking about runtime issues such as buffer overruns or underruns, then more high-level issues like a misuse of an API or use of, for example, a deprecated encryption algorithm like a DES encryption algorithm. So you've got code that was secure at one point, but now the key length is too short. These are things that static code analysis can find. Other issues like hard-coded passwords, for example, or strings. Those are always dangerous things to be using in your code. And then the suspicious behavior class, so things like unused variables or dead code. So these are another part of static code analysis results that we can use to verify the security of the software. So simply by eliminating these or understanding how many you have, you can get a picture of the security posture of the software. So CodeSonar is a static code analysis tool that uses abstract interpretation in order to really understand how the source code is being executed. So each individual possible path through the source code is analyzed, and then it is run against various warning class checkers to determine if there are defects of certain different types. So if, for example, you have an if statement that always evaluates to true, this is obviously a bad idea, because if a developer reads it, they're going to think, oh, a decision is being made here, and there might be some code that should execute. But in fact, because of an error, a typo, let's say, or the use of the wrong variable, or maybe use of a double equals or something, you end up with a if statement that's constantly true or constantly false. So with abstract interpretation, CodeSonar can recognize these situations and highlight that and say this is a bad piece of code. And also, of course, if you have an if statement with a true and a false path, if the false path is never being executed, CodeSonar can alert you to that as well, to that dead code or unreachable code, and say, hey, this code's never going to run. So what that means is that it's not being tested. Because it can't run, it's not being tested. So the great part about static code analysis is, unlike a test tool, which you have to create manual tests, for example, to test the functionality of your program, this tool can automatically, a static code analysis tool can kind of automatically do a bit of an x-ray on the code and say, well, I'm going to look at how the code works, and I'm going to check against this list of hundreds of programming errors that should never be in any program. I'm going to check against that list and see if it has any of that behavior and alert you to that bad behavior. So then as a result of our static code analysis, we can detect any undefined behavior like dead code, like calls to functions that are deprecated, for example, which may or may not have vulnerabilities but shouldn't be used. And that's a good way to start detecting security issues. So I like this slide that says static analysis is easy. It's certainly easy to operate, that's for sure. You already have that. No matter what form it's in, we can take the source code with static code analysis, and we're going to generate a list of warnings from that. So the tool will process for a bit, give you back these results, and these results are very comprehensive and give you everything you need to know to understand the source of a defect. So what kind of defect it is, why it's occurring, how severe or complex we think it is to evaluate this issue, and how it relates to the rest of the program. So this is one of the nice parts about CodeSonar is it gives you such detailed warning information because it really understands how the defect occurred. So if we take an example here of a buffer overrun defect, CodeSonar will categorize that for you and say, hey, this is a security issue. So if you're looking for security issues, you can filter by that. It'll give you the location where it's reporting the defect. So a source code file. So let's say in source.c, line 67, you've got this issue. CodeSonar also provides what we call a severity or complexity score. So this is a reflection of not just the warning class, so not just saying, well, a buffer or overrun is severe, but saying like this particular buffer overrun, the way it occurs, we have a very high confidence that this is a security issue, so we want you to take a look at it first. So if you on a limited time budget, you can use the complexity score to identify the worst offenders and then go into the tool and correct that issue and remove it. CodeSonar also provides an annotation interface, so you can triage these issues. You can assign them to individual developers for them to work on. You can say that, they must be fixed in the current release, or you can defer them to a later time depending on what the purpose of your security review is. I mean, if you're just giving a review and saying, here's the security portion, you can flag these all as to be fixed later. On the other hand, if you've got a corporate policy that says, okay, everything with a certain severity over, 60, a score of 60 should be corrected, then you're sending it off to developers to get it corrected. CodeSonar also tracks issues between builds, so this gives you the ability to present the deltas in your security posture, so you can report to management, the new code we're introducing, has a lot of security vulnerabilities in it, or more, we're increasing in security vulnerabilities. So this might indicate to management they've got to either, for example, maybe invest in training of their developers to help them understand how to code, how to write code that doesn't have these vulnerabilities in it, perhaps invest in different tools or improve their testing methodology to remove these things. And so by tracking across builds, we get that kind of time view of the security of your software. The other thing CodeSonar provides is very detailed path information or execution path information on the defect. So just to look at this issue here, we've got a use after free. So obviously this is something we don't want to do in our code. And CodeSonar, this is the CodeSonar hub interface, a warning display, and CodeSonar is reporting that this file handle F was closed on line 332 of this file, but then is read here on line 281. So here on line 281 is actually where the use after free is reported. And then it's the detailed information explains where the closure is happening. So that's up here at line 332. You can see the little orange marker here put by CodeSonar. So it's saying that in this line of code, this handle WFP is closed. It tells us that WFP was originally equal to the result of this F open operation. So we can actually trace it back to where we created the handle. So this would help us understand, for example, why did I even open this file handle in this code? So we can understand what led us to do the F open. Then we understand, okay, it's closed here, and then someone attempts to use it on this line of code down here. The other thing you'll notice on this screen is some arrows So these arrows are telling you that the highlighted code, which is highlighted in this beige box, the execution path it takes. In other words, if this evaluates to false, this if statement here, and this evaluates to false, and this evaluates to false, all the way these arrows are saying the if pointing out, they're saying that if these all are false, then you get this use after free. So you can see it even here in the message. It says this issue can occur if the highlighted code executes, right? So the idea is it's telling us the path that the code takes so you can quickly understand what leads to this issue. So, likely what we want to do here is we want to check if this pointer is maybe null and throw an exception then rather than try and free it if in fact this code is behaving correctly. On the other hand, we probably have a logic error in our code where we need to explain, someone needs to look at this entire function and understand why it's doing that. So this is really powerful, because if someone just told you you had a use after free on this line of code without understanding why you have that use after free, or why someone has attempted to, or where they've attempted to use the pointer or the file handle, without freeing it, it's basically you're starting from scratch to try and fix this error. The other thing CodeSonar will provide is this visualization between function calls. So this allows us to say, okay, we've got a error, use after free and read book. So we can kind of understand, because again, we had that blank whiteboard, right? So now CodeSonar helps us fill in the whiteboard and say, well, here's where read book exists in your call tree. Here are the functions that are calling read book, and here are the functions that read book is calling. So in this case, I'd probably be very interested in the functions that are calling read book to try and understand why are we opening that function pointer there, and why are we trying to use it after it's closed, to try and understand this architecture of our program. So this is a very, very useful start to our visualization aspect of the security review. So the idea here, and not just this talk, but in general, right, is we need to use multiple tools to generally get a good picture of all of our security issues and controls in our program. So static analysis provides this one view where, without running the code, just by inspecting source code and performing that analysis, we get a list of warnings and understand how those warnings come to pass and come to occur in the code. But of course, when we need to use multiple tools, we need some way to collaborate. So with CodeSonar, we make use of Serif, the interchange format, common interchange format. We can either import or export from Serif. So we can use other tools that find other kind of warnings and import them into the hub so you have one view for reporting purposes, or we can export the results from CodeSonar so that other tools can make use of the results and provide further value in terms of program analysis. So now I'm going to hand it off to John to talk about the Imagix tool suite around reverse engineering. John?
Thank you, Walter. That was a very helpful explanation of how static analysis tools such as CodeSonar collect information about potential security issues in source code. What I'm going to talk about now is how reverse engineering tools are able to help you review this information in the context of the unfamiliar code. So you're able to make judgments about the significance of each of the issues identified, how much work might be involved in improving the security of the code, and possibly, if it's third-party code and you have some choices, is the code a good candidate for use, or should it just simply be discarded? So in essence, the static analysis is used to identify what CodeSonar calls warnings, and then reverse engineering process that I'm about to talk about helps you determine which of those warnings represent actual defects and what should be done about them. Reverse engineering means different things to different people, and I'm going to speak from the perspective of our tool. Imagix 4D is a reverse engineering tool, and we divide its capabilities into 5 areas. The first of these is program understanding. Sometimes that's called program comprehension or source code analysis, and is often what people are referring to when they mention reverse engineering. It can involve everything from high-level architecture understanding about the software down to detailed analysis of specific function or variable dependencies. The second item, delta analysis, you might think of this as a higher level software diff between versions or variants of the source code. But it's a lot more than diff. Rather than simply flag which lines of code have changed, it indicates the impact of those changes at higher levels, from function and variable dependencies all the way up to the software's overall architecture. Design documenting refers to automatically generating accurate, up-to-date design level documentation for existing code. Quality analysis, the fourth point, includes a set of checks to help verify software quality, ranging from software metrics to intertask concurrency checks. And the fifth item, program quality review, is a tool to assist and automate a structured, analysis-driven review of potential issues in software. What Imagix 4D does here is fairly unique, and it's going to be something I'm going to be describing in detail because it's central to how the static analysis results are then imported and used in Imagix 4D. But first I'm going to talk a little bit about program understanding because A, it's a critical building block of the program quality review component, and B, it's quite possible that you will want to have some basic understanding of unfamiliar code before getting to the security review. The challenge with program understanding is that picking up and understanding unfamiliar code is just not easy. You don't know which part of the code to read, and even if you can find the right part, there's just too much to read, and it's often very complex. And even if you could read it all, there's too much information to conceptually integrate. And even if you could pull it all together, there's just too much knowledge to keep in your head. And if you don't have the knowledge, and if you don't have that perspective, you'll be extremely inefficient, and you'll make suboptimal design and programming decisions, and you'll introduce bugs. So you need a tool. And from our perspective, there are two basic aspects for a full program understanding tool. The first of these is visualization, and the second is what we call querying and analysis. So visualization is viewing the information derived from the source code at the right level of abstraction and detail, and in a format that can quickly be absorbed. These views span the range from high-level architectural abstraction to class and function dependencies, all the way down to details of the program logic of individual functions. The second half, the querying and analysis, complements this. It's the ability to focus that visualization on the relevant portions of your software and to modify that focus to follow up as new questions occur to you. Underneath the visualization, querying and analysis of the GUI is what we call an exploration engine, which ties them all together. What's critical is what comes into the exploration engine. In the bottom left, in that yellow area, it's referring to the import of C, C++, and Java source code itself. And the point I want to make here is that precision in generating that database is critical. For C and C++ languages in particular, while there are standards, compilers vary with regard to language and keyword extensions. So different compilers understand the same code differently. And for the sake of accuracy, it's important that the reverse engineering tool understands your source code the same way that your specific compiler does. Above the yellow area in the green there, what you're seeing is the import and integration of additional information, specifically the results from static analysis tools, and we'll also see the import of information from code coverage tools. Walter explained that there's a range of various standards available for testing and compliance. Some of these, as he said, are general quality and safety metrics such as MISRA, CertC, CWE, etc. And some are security related. Many of the checks that flow from these can most effectively be addressed through static analysis, exactly as Walter explained it, where the static CodeSonar generates a list of potential security or reliability issues. Some of the checks require dynamic testing, and when my section here is done, Walter's going to overview that. And then there's a third category, checks that need to be done in what I would call an assisted manual mode. For example, if you're reviewing a requester for a communications channel to confirm that it's properly verified, that's not something that can be done via automated analysis. The code is going to need to be manually inspected by a human. But for all these cases, using a tool to automate this wherever possible is of course very helpful. The first two items, reviewing software at the source code level and mining design level information, lie in the realm of reverse engineering, traditional reverse engineering. And the second two items, recording of steps taken and comprehensive reporting, call for a framework for recording and tracking the review efforts. It's to address this that we've created the program quality review. Within Imagix 4D, we actually call our component here a review tool. The heart of the review tool is the guided checklist. There are two general categories of checks available for these checklists. The top one is the requirements-based checks. These are based on general rules or standards. In other words, these are not an indication of something being wrong. Instead, they reflect a list of what should normally be checked. This could be the standard rules such as MISRA-C, CWE, Search-C, etc. Or it could also be driven by delta analysis that I mentioned when I mentioned the 5 items of the Imagix 4D reverse engineering. The delta analysis identifies control flow changes that have occurred in the software. And then this can be used to focus the review on those parts of the code that could be impacted by those changes. The second set of checks, called testing results, are derived from external tools. And that's what we're focused on in this session today. The key one here, the one you see in green, are items reported by static analysis tools such as CodeSonar. And using Serif, that Walter mentioned, Imagix 4D is able to import the results of CodeSonar for further analysis. Once the checklists are created, the review tool uses the program understanding functionality that I described earlier, the visualization and the querying and the analysis, to examine and analyze the software related to a specific check. The guided checklists automate as much as possible of this process, and not just examining each issue, but in recording observations, making recommendations, tracking results, etc. Let's see how this works. On the left, we see a check. And if you look closely, and this might be hard to see, it's kind of small, but if you look closely, you can see that it's named variables set in multiple tasks. Within that check, there are 2 items or potential issues that are listed. These are warnings that have been flagged by the static analyzer and imported into Imagix 4D as potential defects. And the term that we use for these in Imagix 4D is probes. By clicking on one of the listed probes, you open a probe window in the middle. This displays a bunch of information about the specific warning or that specific issue. And querying and so forth can be unleashed from this. It's from the probe window that the full functionality of Imagix 4D's reverse engineering program understanding and visualization and so forth are applied to that specific warning, that specific what we call probe. On the right, we see a call tree that has been launched. We're able to see how a given variable is used. In this control flow call graph, what we're seeing is how a variable is shared between tasks and where that fits within the control flow hierarchy of the software. As we examine it, we can record any of our findings as notes. These might be suggestions to the engineering for changes. These could include just notes about concerns, etc. And at the end of examining this specific warning, we assign it a priority. It could be okay, meaning that we've looked at it, we've examined it, and it's not something that we really need to worry about. It could be labeled a concern, various levels all the way up to violation, meaning this is serious and needs to be fixed. As you go through this process, including the assigning of priorities, the overall progress is available for tracking and monitoring. And on the tracking level, what we see is an indication of how many probes exist and how many of those probes have been reviewed, and then what priorities have been assigned. The summary also includes these results in an architectural context provided by reverse engineering. So on the left, you can see a portion of what we call the subsystem architecture diagram. The diagram itself shows the layering of subsystems that make up your software. The layering from top to bottom represents control flow dependencies from the top to the bottom layers of your software. Within this architectural diagram, the colors indicate the number of defects or priority probes. A red, yellow, orange, green color scale indicates the relative count of defects in your various subsystems, where red points to the areas of the greatest concerns. Within the context of the architecture, we're able to see the problematic areas and whether they are critical to the operation, how they are linked to the outside interference, etc. The graph on the right also indicates defect counts using the same red, yellow, green color scale, but here it's shown within the context of the function control flow. Now, of course, any defects are going to be of concern, but if you see clusters of reddish functions, you know that that part of the code needs special attention because there could be dependencies between two problematic areas in the code. So far, what I've discussed applies to your initial path at assessing security in unfamiliar code. But you might remember from Walter's portion of the session where he described a situation where you've received a delta and are asked, has our posture improved? So the review tool has a special support for that. This could be a situation where you're checking variants of the source code, maybe a DevOps, for example. And the scenario is that you've got you've been handed a software build, let's call it V1, you run static analysis on it, and then you review those results in the review tool. Then, after some further development efforts, you're handed an updated version of the software, and you need to repeat the process. What's nice about the static analysis is how automated it is. From the review portion involving human interaction, the review tool enables you to reduce the effort by leveraging your earlier reviews of various versions of the code. Taking your results from your review of V1 and applying, where possible, to V2. When probes from V2 match those from V1, then you can carry over the V1 ratings. As you can see in the dialog window on the right, if you do this, you can choose whether to bring over the V1 results and overwrite what is there, or just bring over the results from those probes that you have not yet reviewed in V2. This is done for matches, and if the code in the underlying derivation change is missing because of code changes, then this will not happen. So the reuse of the previous results only occurs where the code has not changed. So in summary, static analysis tools do a great job generating warnings about potential security issues in the source code And then reverse engineering tools enable you to review those warnings to determine which represent actual defects. And that's generally true across the board for reverse engineering tools. Adding a review tool within the overall context of a reverse engineering tool automates many steps of this. It automates importing the warnings from the static analyzer and tying them to the reverse engineering tools, visualization, and querying capabilities. It automates recording observations and conclusions during the review. It automates making these review results available to team members and management, and maybe most significantly, it automates making review results available across versions. So with that, I'm going to turn this back over to Walter, who will talk about another type of tool for the task at hand, code coverage.
Thanks, John. You could just unshare there. Thank you. Perfect.
Mm-hmm.
All right. So that was great. Thanks for walking us through that. I love that color-coded view of the architecture and the call graph defects. That's a terrific way to get a picture of where the problems are in the code. Yeah, so just taking a look here at the code coverage. Yes, let's talk a bit about code coverage. So this is a critical quality metric, right? Because even with static code analysis, of course, which gives us a view into, warnings or defects that are fundamental to good code, what static code analysis can provide, for example, is that your code is actually operating correctly. So in order to do that, you've got to use testing tools that exercise the functionality of your code and verify it against an expected test result. So code coverage tools help you understand how much of my code has actually been tested and reveal areas of the code, for example, where you need to write tests to exercise them, right? And so by adding this, tool and capability to your development, you add another aspect of understanding the quality of your code and understanding where you might not understand the quality of your code because you're not testing it. So one of the uses for static code analysis in this context is to find unreachable code. If you remember earlier, I mentioned that static code analysis runs down all the paths of the execution of the program in a static way, which means if it sees code that it never can find a path or a variable combination or a if statement or conditional that brings you into that code, static code analysis will identify that code as dead code or unreachable. So obviously, if you have unreachable code in your product, no matter how many tests you write, it's never going to be executed. So that means your code coverage can never be 100% because you've got code in the product that's not executing, and therefore no test can exercise it. And that's a place where security vulnerabilities can linger. For example, where perhaps, with the use of some tainted data, you might be able to get code to execute that actually has bugs in it. So we want to make sure that we remove all that code so we can use static code analysis, identify areas that the tool thinks are not going to be executed, and then inspect those areas and remove that code if necessary. And then the second part of this is using code coverage tools now, so that when a code coverage tool reports that only 70% of your code is exercised as part of the test suite, then you know that other 30% should be real code. You've removed all dead code, so you need to write tests that will exercise that code. So what John's going to talk about next is how we can use visualization tools to understand the code coverage on our application. John?
Thanks, Walter. Here what we're seeing, I'm glad that Walter did that nice comment about the colorization, because you're going to see it again here. We're seeing the code coverage information brought into the same architectural diagram and control flow diagram that you saw earlier. Here we're using the same red, yellow, green scale that you saw earlier, but here it indicates how thoroughly code has been exercised in your test runs. In the control flow view in the middle, if you see red indications of low coverage, and they're near other functions that also have low coverage, it tells you that here in particular is an area where you might want to strengthen your test cases. So what I was talking about was this item in the middle, the control flow. again, we're using the same red, yellow, green color scale. And if in the control flow, if you see functions that are in the more challenging area that are red or orange, and they're lumped together, that's going to be an area where you're going to want to, in particular, strengthen your test cases because of the interdependencies between the functions. In contrast, the architecture view on the left indicates the overall coverage of a subsystem. Depending on the architectural context of a subsystem, you might be less concerned about the code coverage for some subsystems than others. So again, this is giving you insight as you consider where you might want to enhance your testing and your test cases. What's new here is the flowchart on the right. It's showing the program logic for one specific function. As you start to review large, complex functions, these flowcharts can start to get pretty involved. What's useful here is that within the flowchart, you're able to see which parts of the function's logic have your test cases not exercised. You can decide whether that's an area that you're concerned about and see how to enhance your tests to exercise that part of the code. What I wanted to mention was that these metrics that we're seeing, the code coverage metrics, or the earlier the static defect metrics, can be combined, that you can define your own sets of metrics that are some combination of the complexity of the code, the amount of code coverage, the amount of static defects, and create some super metric, if you will, some combination metric, and apply those against these same displays. And so you can see, again, those in context, and you can also just get readings of this is an area of real concern where we have low static coverage, or excuse me, large number of defects in the static coverage, and or low code coverage, etc.
Yep, sorry. Thanks, John. No problem. I'm back. So thanks for that. So yeah, the key takeaways, just to sum up our talk here today, reviewing unknown code is hard, right? You've got the whiteboard for architecture, and you've got the thousands of lines of code in front of you. But the good news is there are tools that can help. Static analysis tools can help find warnings and defects in your code that are indications of bad behavior. Reverse engineering is going to help you visualize both those warnings and other defect information in a way that you can consume it, both from an architecture point of view and a call graph point of view. And then code coverage helps you understand how much your tests are covering your code and where you need to write more tests to understand it. Yeah, so I did want to thank everybody at Verifysoft for putting on this great event, and everyone who's attended. Thanks for your time. Also wanted to thank John for doing this presentation with me today. It was really great, John. Thank you. And then I'd like to, we're going to go over to the sessions in a moment to do any Q&A. But before we do that, I'd like to hand it back to our host, Klaus. So thanks, everyone, and we'll see you in the Q&A.